Hi, good day everyone, and welcome back to Curious City. Today we're going to find out how we make Mount Fuji. We're going to learn about geology and how plates collide. Okay, so when we talk about plates colliding, we have about 4 different main ways of these plates colliding. We've got the first one where they move apart from each other and they create a big gap in the middle. Another type where one plate would go under another plate. In this scenario, the plate that's gone under gets very hot and it starts melting and bubbling, and all of that hot material comes up and it pushes up and it causes volcanoes. Another type is where the plates collide and then they create the mountains. And another type is where the plates are side by side and they are sliding against each other. So all over the world, you see that these plates reveal themselves in different geological features. And today we're going to explore 4 different parts of the world. First, Japan and Mount Fuji and the Izu Peninsula. Second, Australia, the Great Dividing Range, the east coast of Australia, and also the Blue Mountains near Sydney. We're also going to look at Cornwall and England and what happens with the moorlands, Bodmin Moor, Dartmoor, Exmoor, and the slate in those locations. And then we're also going to look at California and the San Andreas Fault. Okay, so first we're going to explore how to make Mount Fuji. And for this we're going to go to the Izu Peninsula, which is just a short drive from here. So come with me and then we'll find out lots of information. So the Izu Peninsula actually started much further south than it is today, at the bottom of the ocean as a volcanic chain, because the Pacific plate was going underneath the Philippine plate. So Japan is actually the junction of 4 different plates. If we can see here, to the west we have the Eurasian plate, to the North American plate, to the east the Pacific plate, and to the south the Philippine Sea plate. Right at the junction there, that's where you have the Izu Peninsula and Mount Fuji. So it started about 500 kilometers south of where it is today, and it moved northward, ramming into Honshu. And we can see this over time. Over about 20 million years, the island block moves much further into it, and the Philippine plate is now going underneath the Eurasian plate that is Honshu here. As these volcanoes grew and grew, you see the chain form the Izu Peninsula that we know today. So today's shape of the Izu Peninsula we can see here. We have this volcanic chain, and we have the Suruga Bay and the Sagami Bay, which are where the Philippine plate is subducting underneath the Eurasian plate that is Honshu. Today, at Omuro-san, we are here on the eastern side of the Izu Peninsula. If you form a triangle of the Suruga Bay and the Sagami Bay, you end up finding that the junction with the Eurasian plate is exactly where Mount Fuji is. But Mount Fuji actually has multiple eruptions, and one of the most recent was about 300 years ago, where a big eruption on the side of it occurred. It's actually the side that we're on now, and it was facing this direction, and a lot of material and lava came down the side of the mountain here. Now, Mount Fuji has multiple eruptions. It's this type of volcano, but there are some volcanoes that only erupt once, and that is what Omuro-san is. It only erupts once and then creates all this lava flow. Okay, so here we are at the top of Omuro-san, Omuro Mountain. It's actually a monogenetic volcano. Omuro-san has this conical shape, and it's about a 30-degree slope all around, and that is very similar to that of an hourglass. When it erupted about 4,000 years ago, the lava was very thin and very runny, And what happened is that it overflowed, came rushing down, and created this whole region that wasn't here before. This is on the eastern side of the Izu Peninsula, and it's called the Josaki Coast. So as I mentioned before, when the plates go under, they create these volcanoes, and this happens along the whole plate boundary. And the Izu Peninsula is just part of that whole plate boundary. And you can see in the distance the other island volcanoes along this whole ridgeline. Actually, the composition of Omuro-san is scoria. And scoria is a type of heavy stone that looks maybe similar to pumice, the kind of light stone that we use to get rid of hard skin. But this one is much darker in color and it's much heavier, so it would sink if you put it in water. So unfortunately the clouds aren't cooperative today, but if this was a nice clear day, we would be able to see Mount Fuji, which is directly northwest of Omuro-san, along this valley line, all the way to in the distance. Alright, so now we're going to talk about Australia, and particularly the Great Dividing Range, the East Coast, the Blue Mountains, and what happened close to Sydney. So a very long time ago, Australia broke away from Antarctica. This kind of South Australia kind of connects into Antarctica if you look on a map. And then what happened is that the Australian plate was going underneath the Pacific plate. But then it relaxed and bounced back a little bit, and it caused a little bit of mountains to kind of form along that Great Dividing Range. Over a period of time, that whole area moved over an extremely hot part of the Earth, deeper in the Earth. And lots of material and heat from underneath pushed the Great Dividing Range higher to what we kind of know of today. When this was occurring, there was an eruption that occurred near Mount Victoria in the Blue Mountains, and lots of lava came flushing out all over the Blue Mountains, and it was about 50 meters tall of solidified lava on top of the sandstone that we typically know of the Blue Mountains. Then over a very, very long period of time, the water and the weather and the rain, everything eroded away all of that lava that was once there, and also the sandstone that is underneath, and we get left with the Blue Mountains that we see today. And that's one of the reasons why you see that sandstone line just underneath the top. Now we're going to talk about Cornwall in the southwest of England. And Cornwall is my home, so I'm curious about where it came from. And Cornwall actually has a really interesting history that dates back a very, very long time ago. And it was at the bottom of an ocean, and actually two oceans. You had North Cornwall and South Cornwall, kind of at the bottom of the ocean. And South Cornwall was a deep ocean, and North Cornwall was a shallower ocean. And when the mud settles down on the bottom of the oceans there, obviously some of the dead animals also go down with it. And what happened was, in this very old Earth, this big plate collision occurred, and it crumpled and put lots of pressure on this area in Cornwall. And it created a mountain range. And would you believe it, that mountain range was very similar to the Himalayas that we know of today. And it extended through Cornwall all over North Europe, and also into North America. This was when North America was kind of joined with Europe in a very old Earth. Over a very, very long time, North America moved away, and England kind of separated a little. And then what happened is all the mountains eroded away. When this plate collision occurred and you create a mountain range, the mudstone that was in North Cornwall and in South Cornwall was changed into slate from the high pressure. And in North Cornwall, because it was a shallower ocean, you end up with fossils. And so if you go to the Delabole Slate Quarry, then you can see the fossils there. In the South Cornwall, you end up with not so many fossils because it was a much deeper ocean and not many animals lived in the deep ocean. What happens as well is that when these mountains form, you get a lot of material coming up as well. And this is the granite base of the mountains. And when we look at Cornwall, we can see Exmoor and Dartmoor and Bodmin Moor. And these are big granite blobs left over from the base of the mountains that existed a very, very long time ago. Alright, so now we're going to move across the pond to California and the San Andreas Fault. And what happened there is it was three different plates. You have the North American plate, you have the Farallon plate, and then also the Pacific plate. So the Pacific plate and the Farallon plate are separating from each other, and when you get these separations, you typically also get these shears. This is where the plates slide against each other. Now, this whole junction of this separation and the shearing is actually sliding underneath the North American plate. So if you look over time, you can see that it goes from just only a short part of the California coast, and then it grows and grows and grows. This shearing section grows and grows and grows all the way from Mexico all through to halfway between San Francisco and Seattle. And this is what we know today of the San Andreas Fault. The San Andreas Fault has a lot of energy when it starts moving around, and you can see this in some really interesting locations. One of those is a place called Vasquez Rocks. It's halfway between Los Angeles and the city of Palmdale, which is just north of Los Angeles. And Hollywood used this location to do a lot of filming for Alien Worlds. And you can see that this energy moves and bends and warps the rocks in very interesting ways. And this location is where Captain Kirk from Star Trek fought the Gorn. It's a very popular part of the Star Trek story. Okay, so now we've looked at all those different places, it's really interesting to see how different types of plate collisions and movements can cause very different geological features. So we have things like volcanoes like Mount Fuji, and we have mountains, and then we have the earthquake areas of the San Andreas Fault, the sliding. All these different parts of the world showed very different results of all of these plates moving. And one thing I find really interesting about it is the scale. When you look at these things, like creating Mount Fuji, the size of it is just so awesome. And in America, if you go to the Vasquez Rocks, you can see just the amount of energy needed to really change and warp these rocks. And if you think just as a human standing on these plates, what it must be like when these plates collide. I know it takes a very, very long time for this to happen, but still, it's just very interesting and really shows you the power and the scale of the Earth. So thanks for watching and coming on this journey of curiosity together to learn about geology and how to make Mount Fuji and other parts around the world through plate movements and collisions. We will follow up some parts of the Izu Peninsula in future videos, because actually there's a lot of really interesting geological features around the Izu Peninsula, and because it's local to us, we'll go and explore and share that with you. If you have any comments or suggestions about this video or next videos, topics, if you put those in the comment section below, then we'll respond to those. As always, feel free to like and subscribe and share this. I hope you enjoyed learning about this topic today, and until next time, stay curious.